question, why don't we choose the current number 1 or 1 minus 1? We are free to do that. Yes, we can do that for the linear advection equation, but imagine we don't have the linear advection equation, but we have an equation of this kind, equal to 0, then C is no longer constant. Then we can only choose, we have to choose the current number, then will depend on x. We will have C of x times C of x times delta t divided by delta x. And we have then to choose this smaller or equal to 1 for all. And that means we have to choose the maximum then of the absolute value of the advection speed. So then we can only reach an exact solution for just that special occasion when this is 1. But otherwise the C of x will be less, and we will have then the current number less than 1. So we have to choose then the maximum of the C of x absolute value for all the x that we consider. That is then the maximum of the absolute value of C of x times delta t divided by delta x smaller equal than 1. That we can choose equal than 1 to 1. Then for the maximum we get an optimal solution, but for the others we don't. So therefore it is reasonable that we also study the situation when we choose the current number smaller than 1. And we will get this situation definitely when we don't have this linear equation. It's still linear, of course this is given, but when we have a nonlinear equation that we'll do next week, then we have this ux. So then u can be anything. So then that's the reason why we also study the cases when C, the current number, cannot be chosen equal to 1 or minus 1. So let us continue in our route of looking at different methods to solve the linear advection equation. And the following method has become very popular in recent years. Let's say it started around, say, the 1980s already. In aerodynamics it was used a lot, and is still used quite a lot. But then people also used it for fundamental research, direct numerical simulation of turbulence, simulation in aeroacoustics, and so on. So what is the idea? The idea is similar to that what we studied for the solution of the heat equation. We first do a discretization in space, and then that is, we use the method of lines. We decide on the spatial discretization. When we have done that, we get a system of ordinary differential equations. And those we can solve with any method that we like, and also with Runge-Kutta methods. So let us see how this works. So we are now using the method of lines that we used for the heat equation. We use it now for discretization of the linear advection equation. Method of lines that will be discussed in section 6.2 is now used for the linear advection equation. That was for equation 1. Ut is C ux equal to 0. What was this method of lines? So we do now essentially two steps. First step is that we decide on space discretization, but that we choose one. So decide on space discretization. And get, we have done that, what we call semi-discrete equation. Semi-discrete means half discrete, because the space is then discrete, we have discretized space, but the time is still continuous. We get then this for the equation 1. And the example that we shall choose now is the example that is used quite a lot when we do, for example, direct numerical simulation of turbulence, but then we use a little higher order than we do here, but nevertheless we use center differencing usually, if we want to have the waves represented without dissipation around. So here in that case we choose the center differencing. We could also choose, by the way, upward differencing, no problem. Center differencing. And that means that we use the following. 7, that we approximate the space derivative at grid point xj at a time t by, if we use the operators that we introduced in the beginning in chapter 3, it would be this difference operator, this averaging operator, operating on uj of t. That is then divided by delta x. And this is a complicated way, or a symbolic way of writing the difference between j plus 1, which is a function of t, minus uj minus 1 of t divided by 2 delta x. So we do simply a central discretization of the first derivative. And we write here the t because the time is still continuous. And that is then inserted into the linear advection equation. Inserted into 1, we get then we are at grid point j, and the approximation there is uj. So we get then the time derivative in this kind, at grid point xj, and then we write the rest on the right hand side, and that is then the discretization of minus c du dx. And then we get we use then the approximation that we have written there. uj plus 1 of t minus uj minus 1 of t divided by 2 delta x. So then we get a system of ordered differential equations, because this here is valid for j from 1. We use the notation with the nj. We cannot go to the right boundary, because at nj we would also need nj plus 1, which we don't have. So therefore, we have to stop at nj minus 1. J equals 0 is the boundary condition if c is positive. So then we use then the Dirichlet boundary condition at that point, at x equal at the left boundary, if c is positive. And in general, we can call that the inflow boundary. That is where flow is entering, where or advection is coming from, where it is. And that is then following. It's 59a, I call it. Then we have the u0. Would then be the boundary condition at the left boundary if we have advection from left to right. Then the flow is coming from the left, and we have to give a boundary condition. Characteristics are entering there and carrying in information, so we have to supply that. If we have propagation from right to left, that is what you studied in the last exercise, then we have to give a boundary condition at the right. So then we would give a boundary condition at Nj. It would be then the UB, the right boundary if C is negative. So that would be the inflow boundary. Then we have then taken into account J equals 0 if C is positive, and J equal Nj if C is negative. Now we have to think what to do at the outflow boundary. That is, by the way, also something you have to think of when we do the Lux-Vendrop or the Lux-Friedrichs method. But we said already what we do there, or what we can do. We can use the explicit upwind method at the outflow boundary. So at outflow boundary, we can use, for example, the upwind method, or it's also called upstream differencing. So it would be the following, that at that boundary we would then have, if C is positive, that would be at Nu and J. We would then do the approximation not with the central method, but with the upwind method, which would be U Nj of T minus U Nj minus 1 of T divided by delta X. That would be if we have advection from left to right. If we have advection from right to left, then we would do it at outflow boundary would then be 0. Then we would have to do this similar approximation of the left boundary. And there we would use the upwind scheme that you studied in exercise 6. That is the U1 of T minus the U0 of T divided by delta X. That would be if C is negative. So then we have everything well defined, both for the case advection from left to right, C positive, and for the other case also. So then we have by equation 58, which we have varied at most of the points, we have a system of ordinary differential equations. Taken that and taken either 60A for C positive or 60B for C negative, we have a system to describe all our unknowns. So how the unknowns at the grid points will be related. So let us note that first. So what we get for that, by that is then defined by this, is then a system of ordinary differential equations. It is an initial value problem. So let us now just focus on the case C positive. So then what we have here, this, and for the outflow boundary in J, it would be this case with the boundary condition 59A. Here, they constitute an initial value problem. An initial value problem for the following system of equations, order differential equations. A system of ODEs. So that is important. And that is also called the semi-discrete equation. Semi-discrete equation. Following, call it 61. We have now U is now our vector of unknowns for us it is u1 of t, u2 of t, and so on. And then on the right hand side we have then, we can write it as a function as we are used to when we use a MATLAB function, ODE45 or whatever. Then it calls f of t. Here I call it r from residual. And in here the u is the following. The u is the vector of our unknowns, which is u1, u2, and so on, unj minus 1, unj. So it is all these are then contributing to our unknowns. These are the unknown values at the grid points. Those are now to be determined. And the right hand side is the following. That is the r is the following. And then we have simply to look at this here. That is valid from 1 to nj minus 1. So the boundary condition we use, you will see that. That is j from 1 to nj. So then we have the following. Let's look at it. We have a minus c over 2 delta x in front. So we can write that in front. Minus c over 2 delta x. And then we have here a vector. Now we write what we will have for j equal to 1. Then we will have here u2 minus u0. And u0 is the boundary condition of that case, which we call ua. So we get then u2 minus ua boundary condition. So that is the boundary condition. Let's look at j equal to 2. J equal to 2, we get minus c over 2 delta x. We get here u3 minus u1. u3 minus u1. And this pattern will continue up to the next but last point. And there at nj plus 1 we will get then unj minus unj minus 2. So this is for nj minus 1. That's the last point that we can use this formula for. And the last one, we have to use 60a. So we have to use this one here. unj minus unj divided by delta x. But since we factorized the 2, so we will have then to compensate that here by writing a 2. unj minus unj minus 1. So that is then the right-hand side of this system of ODEs. So that is now a semi-discrete equation that we have, that we get by the method of lines, using central differencing in the interior, and upwind differencing at the outer boundary. So that is step 1. Do discretization in space and get by that the semi-discrete equation, which is a system of ordered differential equations. So the step 2 is to solve this. Now we choose our favorite method to solve that, and that is then the second step. So let's see over here. So that is the second step. First step was discretization in space. Now the second step is the discretization in time. Now we solve the semi-discrete equation which is 61 that we have just derived by an ODE method. You can do that as you like, more or less, but it should be done with some thought. Actually, we have done that already, if you think of it. We have already done it for the following cases. We have done it with explicit Euler method. Explicit Euler method. And that, we do that with the explicit Euler method using the central differencing. What do we get? We get the forward time-centered space. That is what we did in the very beginning. We get the forward time-centered space scheme. That was number 12 that we derived earlier. However, the method is unstable. As you saw in the previous exercise, it's completely useless. It explodes almost immediately. Another example that we just took that yesterday as a remark, that was the implicit Euler method. Implicit Euler method that yields the implicit central method that we saw yesterday. I call it remark 1, implicit central method. That was the number 44. And that method was actually unconditionally stable, first order in time, second order in space, as we use the second order central differencing. That we use first order at the boundary is not so serious. We can afford going one order lower at the boundary. It doesn't hurt the global order. So, we are still continuing on that. This is unconditionally stable. And it is first order in time, second order in space. So that was the method that one can use. It is not the best. You have to work a lot for it. You have to solve linear system, but it can be done. Remark 2 from yesterday was if we solve this system by the trapezoidal method. Remember that we did actually use an average of the center differencing at the old time level and the new time level. That is actually what the trapezoidal method does. So that produced actually then the Crank-Nicolson method. That was number 45, we saw in remark 2 yesterday. And that is also unconditionally stable. And it is in second order in time and also space. So that is a useful method if you want to avoid dissipation error. So it does not have a dissipation error, but it has a dispersion error. But still, you have to solve a linear system. So you have to work more on that to get the same order of accuracy as you get with the Rex-Wendroff method. And now we want to look at another choice to solve this system of equation that we have here with the Runge-Kutta method, the classical one. There are also other possibilities. You can choose whatever you like. And people do that in CFD. I think we'll see an example later on. But when you do want to solve problems, for example, in direct numerical simulation, where you want to have smooth problems, you want to have high accuracy, then it is a good choice to use the classical fourth order explicit Runge-Kutta method. That is the one that we want to pursue here. Classical explicit fourth order. The Runge-Kutta method. Acronym is RK4. And that is what we discussed in actually it was equation 10, sorry, equation 10 in chapter when we discussed the time discretization, and then we already looked at that. If we apply that to solve our system of ODEs that we get from the discretization of an advection equation with the central difference method, we get then the following. We compute now essentially the right-hand sides with different values. The first one is we take it at Tn and we take it at the old time level. When we discussed this for the ODEs, we had here the y, and we used a subscript. But now we have u is a vector of unknowns. We use the superscript to indicate the time. And that is then this vector that we saw just a minute ago. So that is then evaluated with the old time. The time would only come in when the boundary condition is time dependent. Otherwise, we would not have a time dependence. But we write it in this way to have a general. But it is essentially dependent on the solution at the old time level. When we start, it will be the initial condition. So then we compute again the right-hand side, but now we compute it at Tn plus delta T half. And then for the solution that is relevant to us, Un plus delta T half times the right-hand side, which is the slope of our unknown time, K1. And the good thing is, you only need to program this once. You make a function for r, and then you just call the r with, in our case, it is not time dependent, just with the un, and then next time with this. And third time, you call it the following way. It's again at Tn plus delta T half in case you have a time dependent boundary condition, un plus delta T half, and now we take here the K2. And finally, also the K4, the slope in time, again computed, is the residual computed now at Tn plus delta T. Now it is Un plus delta T times K3. So when you have this function r, you just call it 4 times with these different arguments. So it's for the programming, or from the programming point of view, a very neat thing. It looks complicated, but you can, if you have the function r, this is 4 lines in MATLAB. And also the 5th line is the following, that gives you then the solution, that is Un plus 1, the solution at the new time level, is the one at the old, plus the weighted average of the k's, which are the following: K1, grade 1, 2 K2, 2 K3, and 1 K4. So all this together is then the Runge-Kutta method applied to solve this system of ODEs we get for discretizing the linear advection equation. And we can do that for also other problems, so it is quite general. Regarding the truncation error, we can derive that, but it's too tedious. We just think about it, what it should be. We started with the discretization in space with second order central differencing, so it's second order in space. And the Runge-Kutta is 4th order in time. So that means what we get here is a truncation error of the order of delta t to the power 4, delta x to the power 2. So, and regarding the stability analysis of that, we can do a trick. The trick is to look now at a Fourier mode like our solution that is continuous in time. And then put it into the Runge-Kutta, and then we get the stability condition from that. So the von Neumann stability analysis is now the following. Neumann stability analysis that is now of our Runge-Kutta method. This is 62 for solving the system of ODEs 61. So we insert now a Fourier mode that, like our solution in the beginning, is continuous in time. That is the following: 64 u hat k, and now that is the catch. You don't make it discrete, you leave it continuous. Like the solution that we had also when we had the semi-discrete equation. That was also continuous in time. But then we do the same assumption that we have a Fourier mode in space. We insert that for our unknown semi-discrete solution uj of t into the system of ODE 61. And we assume periodic boundary conditions. We can insert it then. 61 is the one that we do in praxis, but when we do now the analysis, we concentrate on the periodic boundary conditions. Then we don't have the problem with the outer boundary. We have always center differencing, so we plug it into 58. And 58 was then du dt. Then that will be then du dt will then be duj dt. That will be then this. We will have time derivative on this. So we'll have then a time derivative on the amplitude u hat of k. So that will be the time derivative e to the I k xj. So that is the duj dt, what we get from there. And on the right hand side we have minus c. And then we have here the center differencing, uj plus 1. That will give us a u hat k of t e to the I k x j plus 1 minus the uj minus 1 will give a similar thing with the ux with the xj minus 1 here. We have again the u hat k of t e to the minus I k x j minus 1. Denominator 2 delta x. So we do a similar thing as we did for the phenomenon analysis, but now with continuous functions, with continuous amplitudes in time. Then we can divide by this e to the I k x j. That goes. Here we get an e to the power I k delta x. Here we get an e to the I k. Let's see. I have an error. Sorry. Here is an error. There should not be a minus here. So the minus was wrong. It's just I k x j minus 1. The minus is here. So but from when we divide by I e to the I k x j, we get here e to the minus I k delta x. So please correct that. There is no minus here, but here the minus is correct. So if we do that, we get the following. So just dividing by e to the I k x j, then we get here the time derivative of the amplitude of the Fourier mode. And on the right hand side we get minus c, and then we just set it e to the I k delta x minus e to the minus I k delta x divided by 2 delta x time u hat k. We can now use Euler's formula. This is cosine plus I sine, this is cosine minus I sine. So the cosine goes, and we get 2 times sine. So from that, we get with Euler's formula that we have the following, 3065. Fourier mode, which is the amplitude of the Fourier mode. And on the right-hand side, we have here a 2I sine. The 2 cancels, and we get minus I C divided by delta x sine of k delta x u hat k. So that is what we get. So when we use the Runge-Kutta method to solve our problem in time, it corresponds to solving the amplitude of the Fourier mode in this form. When we use the Runge-Kutta method, we apply it also then to this Fourier mode. So then we have simply to understand what will be then the stability of this equation when we solve that in time. And that we know, because if you look carefully, you see it is just the test equation. It's just written in a way that we don't see it directly, but it is the test equation. So let us just see that. So that corresponds then to solving the test equation, y prime equal to lambda y. So that is the time derivative of y is equal to lambda y. In our case, where the y in our case is the amplitude of the Fourier mode, and the constant is, now it is imaginary, minus I c over delta x times the sine of k delta x. But otherwise it's just the same. So now we can study the stability for looking at the stability for the test equation for this problem. So we study stability of RK4 applied to 66, or which is the same as 65. And the stability says that this is stable. RK4 is stable if the condition is 67, if lambda times the time step is inside the stability domain of the Runge-Kutta 4 method. And that is equivalent to say, I call that 68. What is lambda delta t? We multiply this by delta t, and we see we get the current number. C delta t over delta x is the current number. So that means the condition is that minus I current number sine of k delta x has to be in the stability domain of the Runge-Kutta form. And that is something that we can check very easily. Now we remember the stability domain of the Runge-Kutta 4 method, real part of lambda delta t and the imaginary part of lambda delta t. And the stability domain was something like this. It's a kidney shape, something like that. So this is the stability domain of the Runge-Kutta method. And what is our lambda delta t? That is what we have here. That is an imaginary number. So what is allowed? Allowed is anything that is then on this line here. Here we can allow anything up to the boundaries, and the boundaries are here minus 2 square root of 2 times I, and here it is plus 2 square root of 2 times. It's about 2.8. So there we can allow our lambda delta t to be stable. So therefore the condition is that our lambda delta t, which is imaginary, has to be somewhere here. So that means we have in our case the it's imaginary, so condition is that minus c sine of k delta x, that is our k, our lambda delta t, that has to be inside this domain. It's imaginary, therefore it has to be somewhere there. And that is satisfied for that is stability condition 6,9, absolute value of the current number. You see that here. The sign we can is at most 1. So if we have that smaller equal than 2 square root of 2, then this will be satisfied. So that is with the Runge-Kutta method, we can go up to current number of 2.8. So that is a stability condition. So with this stability condition, we can get the method stable. Remember the FTCS, over time-centered space, explicit Euler method in time, is unstable, but this one is stable. So that is the basis of many methods that are used in CFD today. Okay, then we have reached the end of the Advection equations. Next week we'll then look at the implicit Burgers equation, and also the week after. This is the basis for the Advection. Okay, so stop here.